Good evening, everyone. This is the week 5 live interaction session for the NPTEL course Computational Fluid Dynamics of our course instructor, uh, Professor Srinivas Jayanti, Department of Chemical Engineering, IIT Madras, and myself, the TA for the live session, Manjunathan, Department of Applied Mechanics, IIT Madras. So, let's see in the course contents. In the week 5, we have you might have covered the basic concept of CFD and also uh, how these approximations, finite differencing approximations are applied, or how the partial differential equations are converted to how the PDEs are converted to algebraic equations. So that finite difference approximations and the schemes related to it have been comprehensively discussed in the uh, fifth week lectures. So with that background, let us move to the today's live interaction section. So I'll be this will be a interactive session. So I'll be reading out the questions and options, and you will get 1 or 2 minutes to inbox your answers. So then we can discuss on the differences. So let's start. First question: in a finite volume method, the integral form of the conservation equation is applied to a control volume. So this is a basic statement, and based on that, the question is, which of the following statement is true about the discretization of the convective term using upward differential scheme? So the question is, you have to, from the options, you have to find one statement which is true for upward differential scheme. Options are: option A, it uses the upstream value of the variable for the convective flux. Option B, it is always second order accurate. Option C, it is unconditionally stable for all flow regimes. Option D, it is equivalent to central differencing for steady inviscid flows. So, from the given option, you can think which one will be the most suitable one relating to upward differential scheme used for the discretization of convective type. You can box your answers. the answer is option A. It uses the upstream value of the variable for the convective flux. So meaning in an upwind differential scheme, it's like suppose, sorry, an upwind differential scheme. Suppose these are three knots. One, so for particular value of here in upwind scheme, this is the upwind side. This is upwind side and this is the wind side. So this value, the upwind value will be having given the importance. So uh, in convective, for the convective term, that should be the case, because the in convective term, the convective velocity or the flow velocity should be the one which will be having given the priority, and that will be the one which will be trans taking the transport. I mean, the property is being transported due to convection, and that convection should be from the upstream velocity current. So option A is the true among the four options given. Next question: which of the following statement is not true about the central differencing scheme? So the question is about central differencing scheme, and the question is for which one of the following is not true. That's or the false statement among the following about central differencing scheme. Options are: option A, it is a second order accurate for smooth solution. Option B, it can be unstable for convection dominated flow with high Peclet numbers. Option C, it is a good choice for diffusive problems with low Peclet number. Option D, it is simple to implement computationally. So which among the following is false? Question is based on central differencing scheme. Okay. Okay, next question. What is the main advantage of using higher order differencing scheme compared to lower order scheme? So the question is, while discretizing, what is the advantage of going for higher order differencing schemes? Options are: option A, reduced computational cost; option B, improved stability; option C, increased accuracy with fewer grid points; option D, easier implementation in complex geometries. So, which of the following is the main advantage of using higher order differencing schemes compared to lower order schemes? You can inbox your answers. Our answer is option D, sorry, option C, increased accuracy with fewer grid points. So, the main advantages of using higher order schemes for discretization is that it will only require a fewer grid points to achieve the same accuracy as lower order schemes, leading to reduced computational workload. Also, higher order schemes can also be used for doing complex geometries also. But the main thing is higher order schemes can grasp or achieve better accuracy than lower order schemes. Lower order schemes, since we mostly use, if we are comparing for a second order or linear or first order, then first linear term or the first order term will be, uh, it will need more grid points to get more accuracy, while higher order terms can achieve uh, better accuracy with lower grid points. Moving on to next question. When discussing the diffusion term in Navier-Stokes equation, which scheme is generally preferred? The question is on discretizing of diffusion term in Navier-Stokes equations. So, for discretizing diffusion term in Navier-Stokes equation, which of the following schemes are preferred? Option A, upwind differencing. Option B, central differencing. Option C, downwind differencing. Option D, any of the above, depending on the flow condition. Can inbox your answers. Which among the following is best suited for discretizing the diffusion term in Navier-Stokes equations? So the answer is option B, central differencing scheme. So diffusion term, as you know, diffusion term is mostly due to the uh, diffusion of our transport property to the surroundings. So best suited method to discretize diffusion terms are central differencing schemes. Whereas upwind scheme or downwind scheme will be used for our convective terms. Moving on to next question. Consider one-dimensional advection equation given by dou u by dou t plus c into dou u by dou x is equal to 0, where c is the advection. Which differencing scheme is second order accurate in space but can be unstable for large Becklet numbers, where Becklet number is given by c into delta x by u. So the question is, while discretizing one-dimensional advection equation, which differencing scheme is second order accurate in space but can be unstable for large Becklet numbers? Options are option A, upwind differencing, option B, central differencing, option C, explicit downwind differencing, option D, implicit downwind differencing. You can inbox your answers. So our answer is option B. From this itself, we can judge second order accurate among the best symbol scheme that will come to your mind for second order accurate is central differencing scheme. But central differencing scheme can create high oscillations, or it can become unstable for high Becklet numbers. This is because of a process called numerical diffusion or artificial viscosity. So while taking central differencing scheme, if there is suppose three nodes, this is I, this I minus 1, this is I plus 1. So in central differencing scheme, the values used for in calculations will be I minus 1 and I plus 1. So the I value will be having less importance, and this can cause the overlines on uh, left hand side term can cause some thing called as oscillations in the solution. So even though it is a second order accuracy, uh, for high Peclet number, uh, it can create oscillations or numerical diffusion. Next question. Upwind differencing schemes are designed to address which issue? Options are option A, rounding errors, option B, inconsistency, option C, convergence issues, option D, boundary condition implementation. So which among the following is addressed or corrected by upwind differencing schemes? Option A, rounding errors, option B, inconsistency, option C, convergence issues, option D, boundary condition implementation. Answer is option B, inconsistency. So upwind schemes are used for uh, preventing or solving the problem of inconsistency in solutions, because like we said for central differencing schemes, in upwind scheme, suppose this is I, this is I plus I minus 1th node, and this is I plus 1th node. Here in upwind schemes, what will happen is like I minus 1 is the upwind node and I plus 1 is the downwind node. So in upwind scheme, suppose OW is the velocity here, E is the velocity here, U is this velocity. So when using upwind scheme, uh, UW will be taken for in place of U while calculating the gradients. So in such conditions, it can overcome the inconsistency by taking the dominant term, and it will also and will be an answer for or will give good results for convective terms. So our answer is inconsistency. Next question. What does CFL number represents? So CFL is current Friedrich Lewis number. So what does this current Friedrich Lewis number, also known as CFL number, represent? Options are option A, the ratio of viscous to diffusive forces. Option B, ratio of time steps to characteristic wave speed. Option C, the order of accuracy of spatial discretization scheme. Option D, convergence rate of iterative solution process. So which among the following is represented by CFL number? The answer is option B, the ratio of time steps to characteristic wave speed. So CFL number is given by C delta T by delta X. So this is the CFL number. So this gives the ratio of time steps to characteristics wave speed, so that our time size should be based on flow speed, that it should capture the particle or flow property should present inside the cell we are being evaluated. So it is the limit for time step that we are constraining through CFL number. Next question. In a finite volume method, the governing equation is integrated over a control volume. Which term requires special treatment for accurate representation of convective fluxes? So the question is on finite volume method. Which term among the below given needs a special treatment for the representation of convective fluxes? Options are option A, diffusion term, option B, source term, option C, convection term or convective term, option D, all of the above. Listener, which among the following requires special treatment for accurate representation of convective fluxes? It's a simple question. The answer is in the question itself. You can easily figure out. The answer is option C, convective tape. Moving on to next question. Which property of the differencing scheme ensures that it approaches exact solution as the grid spacing goes to 0? So, which property of the differencing scheme ensures that it approaches the exact solution as grid spacing delta x goes to 0? Options are option A, consistency, option B, stability, option C, convergence, option D, explicitness. The answer is option A, consistency. So, consistency is the property of the differential scheme which satisfy when delta x tends to 0, the solution will uh, it's like when delta x tends to 0 or grid spacing when it tends to 0, the differencing scheme will ensure that this consistency will ensure that the differencing scheme will converge to or reach exact solution. So our answer is option A, consistency. Next question. Implicit differencing schemes involve solving a system of algebraic equation for the unknown variables at the next time step. What is the advantage of this approach? Options are option A, higher order accuracy, option B, unconditional stability, option C, lower computational cost, option D, easier implementation of boundary conditions. The question is on implicit differencing scheme, and which among the following is the advantage of implicit differencing scheme? Options are higher order accuracy, option B, unconditional stability, option C, lower computational cost, option D, easier implementation of boundary conditions. You can inbox your answers. Our answer is option B, unconditional stability. So when using implicit schemes, we can achieve unconditional stability. Uh, the word unconditional stability means that it doesn't have any limitations on. We don't have to give any particular uh, limitation in the form of uh, any stability criterion. So when for implicit schemes, so this is T1, this is T0. You have again three nodes, I plus 1, I minus 1. So the same three nodes will be here, I will be here, I plus 1, sorry, I plus 1, here I minus 1. Suppose for the values, particular value for I in the uh, T1, next time step is calculated from entirely the values from the previous time step, that is this time step, then such uh, schemes are called explicit schemes because all the values are explicitly known. We know every values of the terms that we are used for computation. But if we are using some terms from the current time step itself, then such schemes are called implicit schemes. So these kind of implicit schemes will be uh, implicit schemes will provide unconditional stability because they don't have much restrictions, and also we don't have to store the values from the previous time step. So there are more than one advantages for using implicit schemes. Okay, moving on to next question. In a finite volume method, the integral form of conservation equation is discretized over a control volume. What is the general form of the discretized equation for a steady state advection diffusion problem? So the question is on from the following. We have to choose the right equation representing steady state advection diffusion problem. Options are option A, integral of rho v minus gamma dou u by dou x times dA is equal to 0. Option B, dot times rho u by dou t plus dot times gamma dou u by dou x is equal to 0. Option C, dou u by dou t plus c into dou u by dou x is equal to 0. Option D, u of I plus 1 minus u of I minus 1 all divided by 2 delta x is equal to 0. So, which among the following gives discretized equation for steady state advection diffusion problem? You can inbox your answers. Your answer is option B. So in this time, both convection and diffusion fluxes as properly represented. Moving on to next question. Lax-Weintraub scheme is a second order accurate upwind scheme. What is the numerical stencil or grid points used for approximating the spatial derivative of 1D advection equation? Question is on the stencil of Lax-Weintraub scheme. Options are I minus 2, I minus 1, I plus 1. Option B, I minus 1, I plus 1, I plus 2. Option C, I plus 1, I plus 2, I plus 3. Option D, I minus 1, I plus 1. So basically, uh, uh, the question is on stencil, which all the grid points are being used for approximating the spatial derivative in 1D advection equation. Here, you see, uh, uh, there's little more technicalities in this question. If you see only this spatial terms, this much I minus 1, I plus 1, only these terms exist. But actually, uh, the Lax-Weintraub for Lax-Weintraub scheme, the stencil looks a little more complicated or little more complex because if you see here, this is the stencil for Lax-Weintraub scheme. Here you can see I minus 1, I and I plus 1 is taken, but at the nth step or nth time step. Also, I at n plus 1 step is also involved. So these 4 points are there. But technically, from the given options, we can choose D. But actually, it should be none of them because something like this should be there. So the answer can be taken as I minus 1, I and I plus 1 since these are the only spatial times, spatial nodes used. So technically, it has points from n and n plus 1, both time steps. a stencil for laxment of skin. Moving on to next question. Consider the steady state heat conduction equation in one dimension. Dou square T by dou x square is equal to Q by K. Which differencing scheme is first order accurate and unconditionally stable for any mesh spacing? So the question here is, for solving one-dimensional heat equation, which among the following options will be first order accurate and unconditionally stable? Options are: option A, central differencing; option B, upwind differencing; option C, forward differencing; option D, implicit backward differencing. You can try to answer the question. You can inbox your answers. The answer is option D, that is uh, implicit backward differencing. So this is also known as Euler's method. Mostly implicit schemes, both forward and backward Euler is of first order accurate and accurate first order accurate in time and unconditionally stable for different type of problems. If you see here, the other options are central differencing scheme, upwind, and forward differencing scheme. So central differencing scheme is unconditionally unstable. It will be always unstable for uh, uh, this kind of problems. And upwind scheme and forward schemes will be conditionally stable. So we have to set the mesh size and time stepping in according to current number limitations. Then only these two become stable. Whereas implicit schemes, implicit forward, implicit differencing, or backward implicit, that is the Euler methods, are unconditionally stable and first order accurate for diffusion type of problems. Moving on to next question. Next question is on uh, in a finite difference method applied to one-dimensional Laplace equation, the central difference approximation for the second order derivative at point I is which among the following? So the question is, uh, The question is for an one-dimensional Laplace equation uh, using discretized using central difference approximation. Which among the following is the second order derivative at point I? Options are if the transferable property is phi. Options are option A phi of phi at I plus 1 minus 2 times phi at I plus phi at I minus 1 the whole divided by delta x square. Option B phi at I plus 1 minus phi at I divided by delta x. Option C phi at I plus 2 minus 4 times phi at I plus 1 plus 6 times phi at I minus 4 times phi at I minus 1 plus phi at I minus 2 the whole divided by delta x square. Option D phi at I minus phi at I minus 1 divided by delta x. So the question is which among the following is the second order derivative at the point I for one dimensional Laplace equation? You can inbox your answers. Our answer is option A phi at I plus 1 minus 2 times phi at I plus phi at I minus 1 divided by delta x square. So for central differencing scheme, it's a combination of forward and backward differencing scheme that as we have discussed in previous interactions. So the when clubbing the forward difference and backward difference, it will the central time will be minus 2 times phi at I will be here. So this is the equation for central differencing scheme for second derivative at I. Next question. It's on general PD types. The question is which of the following cases is generally modeled with an elliptic PDE? So we know there are three different types of partial differential equation, that is PDE. Uh, they are parabolic, elliptic, and hyperbolic. So there are three types of PDEs. So the question is which among the following cases will be most generally modeled with an elliptic type of PDE? So the options are option A steady state heat transfer, Option B, propagation of a standing wave. Option C, Fick's second law. Option D, traffic flow. So, which among the following is most generally modeled with an elliptic type of PDE? You can inbox your answers. Okay, our answer is option A, steady state heat transfer. So, in steady state heat transfer, uh, there won't be any time variant time. The heat transfer is mostly due to diffusion or either because of presence of a source. So this steady state heat transfer equations are mostly modeled with a Laplace equation, and Laplace equation is by definition an elliptic PDE. So uh, steady state heat transfer is the elliptic PDE. Steady state heat transfer is the case where elliptic PDE is used. Moving on to next question. In a finite volume method, for the Laplace equation, the integral form is discretized over control volume. What is the general form of the discretized equation for a uniform mesh? So this is a continuity kind of question from the previous question. So here, what is the discretized form of uh, Laplace equation in a uniform type of mesh? Options are option A, phi at I plus 1 comma j minus phi at I minus 1 comma j plus phi at I comma j plus 1 minus phi at I comma j minus 1, the whole divided by 4 times delta x is equal to 0. Option B, dou, dou by dou t of rho phi plus uh, dou by dou x of gamma times dou phi by dou x is equal to 0. Option C, 4 times phi 4 times phi at I comma j is equal to phi at I plus 1 comma j plus phi at I minus 1 comma j plus phi at I comma j plus 1 plus phi at I comma j minus 1. Option D, phi at I plus 1 comma j minus phi at I comma j divided by delta x is equal to 0. You can inbox your answers. The question is pretty easy to solve from the, if you check the option itself, we can understand the options itself gives away the answer. Okay, the answer is option C. Uh, 4 times phi at I comma j is equal to phi at I plus 1 comma j plus phi at I minus 1 comma j plus phi at I comma j plus 1 plus phi at I comma j minus 1. So this is the stencil for with a uniform grid. So if you see, it's like two sections if you are consider. So this itself, if you remember the previous question, so here itself, uh, the central time will be minus 2 times phi at ij will be there. So when we consider a two-dimensional domain, then there will be two of such terms. So when it is taken to the other side, it will be 4 times phi ij. That's how it is represented. Also, if you look at the options, it's like here it is the question is like here if you see there is no time telling like uh, speaking about this phi ij. So that phi ij I comma j phi it I comma j is missing here. So this is wrong. And as you can say, this is not a discretized equation. Then here itself there is only one side, just uh, forward differencing method. I mean, discretization is only here. So all this can be neglected. From the options itself, you can easily choose the right answer, option C. Moving on to next question. Which of the following statement is not true about Poisson equation compared to that of Laplace equation? So the question is between comparison of Poisson equation and Laplace equation. Options are option A, the Laplace equation includes a source term. Option B, both equations govern potential flow. Option C, both equations are elliptic in nature. Option D, both equation has similar boundary conditions. So which among the following is not true? You can inbox your answers. So from the option itself, we can understand the question is about not true about Poisson equation. So first uh, option itself is saying about Laplace equation, and that is wrong also. So we can eliminate this option. I mean, sorry, we can choose this option. Wait one. So this is only saying about Laplace equation, and Laplace equation does not have a source term, as we have discussed in previous questions. Uh, Laplace equation is a represents steady state equation, steady state heat transfer. So for steady state heat transfer, the source term is not there. So in such a case, this option becomes not true, and also it's not talking about Poisson equation. And if you see the other options, option B, both equations govern potential flow. That is true. Uh, that's a true statement. And both equations are elliptic nature. That's also true. Both Laplace and Poisson equations are elliptic type of equations, partial differential equations. And mm, next question, I mean next option, both equations have similar boundary condition. Since both are of similar kind of equation, that is, both are of elliptic in nature, then obviously their boundary conditions will be similar. So all these three, option B, C, and D are true. So our question is to find which is not true. So option A is the uh, uh, right answer, or the false statement among the list. So this is the difference between Poisson equation and Laplace equation. So Poisson's equation, there is a presence of source term is present in Poisson equation, whereas in Laplace equation, it's deals with the steady state without any source term. So that's the difference between Poisson equation and Laplace equation in relation to this statement. Moving on to next question. Consider a channel flow simulation. The pressure field is governed by the Poisson equation with no slip velocity boundary condition at the walls. Which of the following statement about the pressure discretization is not correct? Options are: option A, pressure can be directly set at the wall boundaries. Option B, pressure gradient at the walls needs special treatment due to no slip condition. Option C, the pressure equation needs to be solved only for the interior points. Option D, the discretization scheme for pressure should be the same as for velocity. So the question is about discretization of pressure time in a channel flow simulation. You can inbox your answers. Your answer is pressure can only be directly set to wall boundaries. So this is the wrong statement among the others. All other statement in this context is true or correct. Moving on to next question. Consider a square domain discretized with a uniform mesh. The number of unknowns in the discretized system of equation for the Laplace equation with Newman boundary conditions will be which among the following. Options are equal to the number of grid points. Option B, less than the number of grid points due to boundary conditions. Option C, more than the number of grid points due to ghost points. So, which among the following will be true in case of a square domain discretized with uniform mesh and having Newman boundary conditions for solving Laplace equation? You can inbox your answers. Okay, so here the question is on square domain discretized with a uniform mesh and having Newman boundary conditions. So Newman boundary conditions can be set either by implicit method or explicit method. So the explicit way of expressing Newman boundary condition is by employing ghost points. So due to ghost points, that because we will be creating imaginary or non-existing cells only for computation at the boundaries when a Newman boundary condition is there. So option C is the right answer. So this at the boundary we will create another set of uh, points called ghost points at the periphery only for storing some values and to make the computation easier or computation the way it is supposed to happen. So option C, due to this presence of ghost points, the number of grid points will become more than what there should be. Moving on to the next question. In a finite volume method for 2D Poisson equation, the source term F is integrated over the control volume and discretized using a suitable averaging scheme. The question is a true or false question. You can answer A or B. A is true, B is false. Is the statement above such statement about discretization of two-dimensional Poisson equation with source type F is true or false? Answer is option A, true. For while when the source time is present in finite volume methods, this finite volume methods, this source times will be added to the side and integrated over the control volume, so that some portion of this source time is added to every element. So our statement is true. Moving on to next question. In a finite volume method applied to a Poisson equation, what represents the source time S in the discretized equation at a control volume? So this question is a continuation of the previous question. They said the what uh, what is that the source term actually represents in a Poisson equation. Option A, the net flux of dependent variables across the control volume boundary. Option B, the change of dependent variable over time. Option C, the gradient of dependent variable at the control volume center. Option C, the boundary condition value at the face of a control volume phase. You can inbox your answers. So, what is the source term in Poisson equation? Or what is the source term actually represents in a Poisson equation discretized over a control volume using finite volume method? Answer is option A, the net flux of the dependent variable across the control volume boundary. So in the Poisson equation, represents the external contribution or the addition or the quantity, addition of the transferred quantity into the control volume. So our answer is option A. Moving on to next question. Which of the following statement about the convergence of discretized Poisson equation is generally true? So the question is about convergence of discretized Poisson equation. Options are option A, the solution always converges to the exact solution regardless of the mesh size or differencing scheme. Option B, increasing the mesh spacing delta x and delta y guarantees faster convergence. Option C, a finer or smaller delta x and delta y usually leads to more accurate solution and convergence. Option D, a higher order differencing scheme always improves faster convergence. So which among the following is true about the convergence of a discretized Poisson equation? You can inbox your answers. So if you analyze the options, it is pretty easy. So the first statement says that the solution always converges to the exact solution regardless of the mesh size or differencing scheme. So from the statement itself, we can understand that it is wrong because the convergence always depends on the mesh size and differencing scheme. Also, the option B says that increasing the mesh spacing guarantees faster convergence. We can say that increasing the mesh spacing won't guarantees won't even guarantee convergence because increasing the mesh spacing creates lower number of mesh elements or less number of mesh elements. This reduces the chances of convergence itself. Not even it won't even converge itself. So option C, next going to option C, a finer mesh that is smaller delta x and delta y usually leads to a more accurate solution and convergence. So this is true because a finer mesh helps in more accurate solution and also convergence. When the mesh is finer, the time taken for convergence may be long, but it still helps to get a more reasonable or accurate solution, and also it guarantees convergence. Moving on to option D, choosing a higher order differencing scheme always improves faster convergence. It's like uh, moving to a higher order differencing scheme uh, reduces the number of elements, but while it won't always give faster convergence. So the option is option C. So the process of making finer mesh is called mesh refinement. So that uh, an optimum level of refinement is needed for reasonable solution and convergence. So higher order schemes can capture more details, but while uh, we can't say that it will always give faster convergence. So it can sometimes give slower convergence also. Moving on to next question. Compared to central difference scheme, how the lag scheme addresses the issue of non-physical oscillations, that is wiggles, in the solution for advection problems. Options are: it introduces numerical viscosity damping the oscillations. Option B, it is inherently unconditionally stable. Option C, it requires finer mesh for accurate solutions. Option D, it is less computationally expensive. So, which among the following is the advantage of lax scheme over central differencing scheme for addressing the issue of non-physical oscillations for advection problems? You can inbox your answers. So our answer is option A, that it introduces numerical viscosity. Uh, it is like artificial numerical viscosity, numerical diffusion. and is called as numerical diffusion. And this is actually a negative trait because it can't capture the sharp gradient or sharp change in the value of the transported property, but it gives more like a gradient or some rather than taking suppose our this is the uh, property phi, how the property phi varies over time. Then if there is a numerical diffusion, then the solution will be something like this. So rather than taking this sharp jump, it will having some it will take a somewhat slope. Some uh, portion will be uh, not captured by the solution. So that is the numerical viscosity. It's generally a negative term, but for mm, in the case of advective uh, problems, here the problems is advection problem. So for advection problems, this negative uh, uh, property will actually help. So it will help in damping the oscillations, which will be present when using other. We have discussed that the central differencing scheme will create high amplitude oscillations in while solving. So such kind of issues can be overcome by using the property of numerical viscosity. Next question. Compared to upwind differencing scheme, what is the disadvantage of Lax-Ventropf scheme? So the question is on comparison of upwind differencing scheme and Lax-Ventropf scheme. So what is the disadvantage of Lax-Ventropf scheme compared to upwind scheme from the options given below? Options are: it is inherently second order accurate. Option B, it is more computationally expensive due to its complex stencil. Option C, it is not suitable for steady state problems. Option D, it requires knowledge of the flow direction. So which among the following is the disadvantage of Lax-Ventropf scheme compared to upwind differencing schemes? Our answer is option B. It is more computationally expensive due to its complex stencil. We have seen their stencil of Lax-Ventropf scheme in the previous question. So the Lax-Ventropf schemes needs uh, all the data from previous steps to calculate the present value. So it is computationally more expensive as we have to store all the values of the previous time step, previous iterative step. Moving forward, next question. Which of the following factor does not affect the stability of an explicit finite differencing scheme? Options are option A, grid spacing, option B, time step size, option C, current number, option D, boundary condition. So, which among the following does not affect the stability of an explicit finite differencing scheme? You can inbox your answers. The answer is from the options itself, we can easily uh, find out the answer. So this option C is the current number. So it will be the first thing came to our mind when we are talking about the stability. So stability is mostly related to current number or current Frederick Lewis criterion. So so current number is directly related to stability. So it will affect the stability. So if you see here delta t and which is option B and delta x are there inside current number. So all these three will affect the stability of explicit finite difference scheme, whereas boundary conditions may not directly affect the stability of the scheme because boundary conditions are helping to solve the thing. Uh, it won't the it won't it will only affect it the solution it is when if it is drastically changed, but other three conditions, that is delta t, delta x and current number, will uh, directly affect the stability, whereas boundary condition, even though uh, it has effect on solution or solving process, it does not have that much role when compared to other three options listed above. Moving on to next question. This is the main purpose of mesh refinement in specific regions of CFD domain. So the questions on mesh refinement. Options are option A to reduce computational cost, option B to capture complex geometry details, option C resolve high gradients and boundary layer physics, option D ensure mesh conformity. You can inbox your answers. So from the options, if you see, option A is wrong because when mesh refinement happens, the computational cost will go up. It won't reduce it. So option A is wrong. Option B, capture complex geometry details. That is true in case of mesh refinement. And option C, resolve high gradients and boundary layer physics. That is also true for mesh refinement. Option D, ensure mesh conformity. That's also true in case of mesh refinement. So option B, C, and D are true in case of mesh refinement. But whereas the question is on main purpose. So main purpose is option C, to resolve high gradients. So there will be regions in our mesh of uh, regions where our transported property will be varying very drastically. So these high gradients can only be captured with a highly refined mesh. So these sharp changes, for capturing the sharp changes in a very small region, we need to have that much refined mesh in those regions. So our answer is option C, which is the main purpose of mesh refinement. Moving on to next question. What is the key concept behind the mesh independent studies in CFD? Option A, analyzing the mesh quality based on element shape. Option B, verifying that simulation remains unchanged with increasing mesh density. Option C, validating the CFD model against experimental data. Option D, reducing the overall memory consumption of the mesh. So the question is on key concept behind mesh independent studies in CFD. You can inbox your answers. So the key concept of mesh independence is like independence from the mesh properties. That is the key independence. So from the name itself, we can understand. So our answer is option B, that verifying that the simulation results remain unchanged with increasing mesh density. So when mesh density increases, what is mesh density? Mesh density meaning uh, the number of elements in a unit volume of mesh. So increasing mesh density means the number of increasing the number of mesh elements in that unit volume. So such things showing that uh, when the refinement is refined more and more, we can see that the calculated flow property, uh, fluid property will remain unchanged after uh, some value, or the less the changes will be drastically reduced. So such condition is called mesh independence. So that is what we are doing mesh independent studies or mesh refinements. So that is all for today. Thank you for joining the course interactive section. Thank you all.